Welcome back, everybody. In this video, we'll be finishing up section 4.2. So we have looked at the addition property for probabilities. And what we're going to look at next is a couple of examples, and then we'll go on to look at a rule for complementary events. So first, let's take a look at a couple of examples. So in this, we're to decide whether the events are independent or dependent, and then find the probability that both events A and B occur. So we're just going to try a couple of these. So for 5, it says, when a month is randomly selected and ripped from the calendar and destroyed, it is July. And then B, when another month is randomly selected and ripped from a calendar, it's November. So here, those are going to be independent or dependent. Okay, so let's think on that for a minute. So the probability of A occurring is going to be 1 out of 12. July is one of the 12 months. And then for B, when a different month is randomly selected and ripped from the calendar, it's November. So the calendar only has 11 months left, right? Because July has already been ripped from it, and so we've got just 1 out of 11 chance for it to be November. So knowing that A has already occurred will affect the likelihood that B occurs, and so that makes them dependent. Okay, and then the probability of A and B is going to be the probability of A times the probability of B, given that A has occurred. The probability of A occurring, we saw, was 1/12. And then the probability of B occurring, given that A has occurred, is going to be 1 out of 11. So if A has already happened, that is, there was July, there's taken out the first time, there's only 11 months left, out of which 1 is November. So then that's 1 in the top, and then 11 times 12 is 144 minus 12, 132. 1 out of 132. Okay, here A, 6, when a baby is born, it's a girl. There's a 1/2 chance of that occurring. B, when a second baby is born to a different family, it's also a girl. Its probability is 1/2. Those are going to be independent. Just because the first family had a girl doesn't mean anything about whether the second family will or will not, right? So the two are going to be independent. And so the probability of both occurring is going to be just the product of the two probabilities. And so it will be 1/4. All right, so that seems good for those. So then moving along, we had talked about the addition rule. I wanted to go on to the rule for complementary events. We talked about an event and how the complement is related. The complement of an event is basically not having the event occur. So if A is, you roll a die and you get a 4, okay, then the complement, which we could denote with a little bar on top of the A, or a little superscript C, or a tick mark, all of those could mean the complement, depending on whose book you look in or where on Google or YouTube you are. Our book uses the horizontal bar on top, and so I'll probably stick with that. Those would mean getting anything other than a 4, so it's not a 4. Okay. So the rule for complementary events goes like this. It looks like they've given 3 equations here, but they're all just algebraic variations on the first one. It says the probability of A occurring plus the probability that A doesn't occur is going to be 1. If you solve for the probability of A complement, it's 1 minus the probability of A. If you solve for the probability of A, it'll be 1 minus the probability of A complement. So to see where this comes from, we're going to use our rule for one event or another, which is the addition rule. So looking at the left side, the probability of A or A complement occurring. Remember that A and A complement are basically kind of the opposites of one another. So it's going to happen that you either will have a or you won't. Okay, if you roll the die, you either will get 4 or you will not get a 4. Okay, today's either Tuesday or it isn't. Okay, so that is sure, right? It is true, it is always true that either A will happen or it will not. Okay, and so we've discussed how anything that has a definite probability, anything that is certain to happen, will have probability 1, right? And so that accounts for the part I'm marking here in yellow, okay? So the probability of A either happening or not, well, that's definite. It's going to be probability of 1, okay? So then continuing on, looking at the right side, using our OR formula, that means that the probability of A or A complement is the probability of A plus the probability of A complement minus the probability they both occur. But as you know, A and A complement are mutually exclusive, so their probability is going to be 0. So then it just simplifies down to the probability of A plus the probability of its complement equals 1. Okay, so examples. So let's say that you roll a die, and A is the event that you roll a 4. We're going to find the probability of A and its complement. Okay, so the probability of A is going to be 1/6. The probability of A complement is going to be 1 minus the probability of A, and that's 1 minus 1/6, and that's equal to 5/6. Okay, and so thinking about what's possible with a die, the numbers 1 through 6. This example can seem like I'm just playing around, right? Because you probably looked and thought, okay, well, sure enough, if you roll a 4, then one number is a 4, and then the other 5 numbers are not 4s. So yeah, it's 5/6. That's easy. So why bother using the formula? The formula is really useful when thinking of that kind of direct approach is harder. Okay, but I wanted to start with an easier example. Okay. Okay, another example. We're going to pick a card from a deck of cards, and we want to know the probability that it is not a 6. Well, if it's not a 6, then it's an ace or a 2 or a 3 or a 4 or a 5, 7, and so on. So that's a lot of possibilities, and so we don't want to consider all those. So the probability that it is not a 6. Okay, so we want to think about the complement of not being a 6. The complement of not being a 6 would be a 6. So this would be 1 minus the probability that it is a 6. Okay, and the probability that it is a 6 is easier to calculate. So let's do that. 1 minus the probability that it is a 6. There are 4 6s in 52 cards. The 4 52nds simplifies to 1/13. And so that will give you 12 out of 13. Again, that's not too bad to think about just doing this one directly. You could think, okay, well, 2 through 10 plus ace, jack, queen, and king, that's 13 numbers. And the 6 is, or 13 cards. The 6 is one of those. Take that out, there will be 12 left, so 12 out of 13. Okay. All right, so here this next example will be a little bit more involved. So here there are 3 coins tossed. If you like, you can make one a penny, one a nickel, one a quarter. Okay, so there's 3 coins tossed. We want to know the probability of getting at least one tail. So at least one tail would be 1 tail, or 2 tails, or all 3 tails, right? So that's kind of 3 different possibilities. So, and they're all mutually exclusive. You can't simultaneously have exactly 1 and exactly 2 and exactly 3. Right? So we could use the OR formula, but it'd be kind of complicated to figure out what all those possibilities are. So instead, let's think about what happens if this fails to be true. If you don't get at least one tail, notice that that doesn't mean that it's 2. At least 1 is 1, 2, or 3. If that doesn't happen, that means there are no tails. So at least one tail, the probability of that occurring will be 1 minus the probability of getting no tails. And that's easy to figure out. Okay, so 1 minus the probability of no tails. So we need to think about how many ways the 3 coins could come out. There are 8 possibilities, and there's only one that has no tails, and it will be all heads. So there's a 1/8 chance of getting no tails. So 1 minus 1/8 is 7/8. So there's a 7/8 chance of getting at least one tail. Okay, to make that clear, I'm going to make a tree diagram that kind of illustrates what all the possible outcomes were. So our first coin, let's say it was a penny. It could have been either heads or tails. The nickel, I can't remember if I said a nickel before, but that's okay. The nickel could come out either heads or tails, and that is independent of how the penny came out. And then the last one I think I said was going to be a quarter. Okay, the quarter has no memory or knowledge of what the penny or nickel are doing, and so it has 2 possibilities no matter what. It could come out heads or tails. And so we're going to end up with, if you're looking ahead, you're going to see that we're going to have 8 possibilities. And they range from going across the top, HHH for all 3 heads, all the way down to TTT for all 3 tails. Okay, let me go ahead and write these out. All right, so there's all the 8 possibilities written out just as little triplets there. So we wanted to know the probability of getting at least one tail. At least one tail would be all 7 of these options. The only way to not get at least one tail would be having that 1 out of the 8 cases where it was all 3 heads. So that accounts for why the probability of getting at least one tail is 7/8. All right, continuing onward, we want to try another example. This one is different. So this one, the story is about pre-employment drug screening results. So as you know, when people go to apply for a job or going through the hiring process, they can take a drug test, and there's a couple of possibilities. It may be that the person actually uses drugs, or maybe they don't. And then there's a couple of different possible test results. The test could come out either positive or negative. So that leaves to 4 possibilities, ranging from a positive test to a person who uses drugs, all the way to a negative test for someone who does not use drugs. So there's names for these: true positive, false positive, for whether the test comes out positive. Of course, it's going to tell you it's positive, and then it's either true or false, depending on whether the person actually uses drugs or doesn't. And then the test being negative, it could be false or true. If it's a negative test result when the person actually uses drugs, that is, the test fails there, that's false. And then a true negative would be where the test comes out negative and the person actually doesn't use drugs. So this is a set of 1,000 results of some drug screening, and so we want to answer some questions based on this data. Okay, so here it says if 2 of the 1,000 test subjects are randomly selected, we want to find the probability that they both had false positive results, and then we want to know if it's unlikely to randomly select 2 subjects and get 2 false positives. So the false positives are these 90 people who are not drug users and yet who tested positive. So we want to know whether they're both false positives, the 2 of these people. And then we're doing the selections in 2 ways, either with or without replacement. We're going to do it with replacement first. So that means that either way, we need the probability that the first is a false positive and the second is a false positive. Right? The word "and" in there is what's telling me I need to multiply probabilities. As you know, for "or," we use the addition formula, and for "and," we multiply. So first and second need to be false positives. So for part A, For part A, we're doing this with replacement. If it's with replacement, that means that the draws are independent. That is, how the first person came out doesn't affect the second person. Okay, so the first one, out of 1,000 people, there were 90 false positives. And then when we go to select the second person, there are still 90 false positives out of a pool of 1,000 people. Okay, so let me make that a decimal for you. So that's 0.0081. All right, for part B, the story and everything is very similar. The only change is that we're making the selections of the two people without replacement. So when we go to choose the first person, there's 1,000 people, out of which there are 90 false positives. And here's where the difference comes in. When we're doing this one without replacement, that means that the first person, we've already taken that candidate out and set them aside. When we go to do the second person, that means there are only 999 people left. And we're assuming that that first person was one of the false positives. So there are only 89 false positives remaining. So let's see what that works out to be. Okay, 0.0080. Okay, so here it didn't turn out to make that much of a difference. And if you think about it, that should make sense. We're talking about 1,000 people, right? So picture a really big room with 1,000 people in it. All these people have taken these tests. In the first case, part A, where we select the first person, we find out the probability they're a false positive, and then they go back into the room. Okay, and then we do the second person. So there's a chance that that first person could be selected again, but out of 1,000 people, that's pretty small. Okay, in the second case, we're telling that first person to wait outside while we go select the second person. So the second person or the first person could not be selected again. So that changes the probability of getting a second false positive because one of the false positives has been removed. Since there are so many people in there and relatively few false positives, that's why these two probabilities came out pretty close to one another. We'll see that come up again. Okay, so more examples. So here, assume that Google hires employees on different business days of the week. So that's Monday through Friday with equal likelihood. We're going to answer some questions based on this. So it says if two different employees are randomly selected, what is the probability that they're both hired on a Monday? So there's nothing in the story here that would indicate anything about how the first person being hired on a Monday or maybe not influences the hiring of the second person. So it's reasonable to conclude that those are independent events. So since they're independent events, we can just multiply their probabilities because we're saying both here means the first one and the second one. It's and we're going to multiply. So it's Monday through Friday. So there's a 1 in 5 chance that the first person was hired Monday, and then a 1 in 5 chance that the second person was also hired on a Monday. So that's a 1/25th chance. Okay, so now for part B, if two different employees are randomly selected, what is the probability that they're both hired on the same day of the week? So this question is a little different because we're not asking it to be Monday. It could be any day of the week. It just needs to be the same for both people. So there's at least two ways of looking at it. Probably the simplest way, I think, is to take the first person's day of the week to be fixed. Whatever day the first person was hired, let's say Thursday, and then what is the probability that the second person had the same hire day? So that will be a 1 in 5 chance. Okay, so the probability is just 1 in 5. Okay, if you didn't like that or find that confusing, here's another way of thinking about it. So part B still, okay? If two different employees are randomly selected, we want the probability that they were both hired on the same day of the week. that would be both Monday, Tuesday, Wednesday, Thursday, or Friday, right? Any of those 5 days. And each of those possibilities is mutually exclusive, right? Your hire date can't be both Monday and Wednesday, okay? For example, it's got to be one day only. So these options are all mutually exclusive. So we're going to figure out the probability that they're both hired Monday, which we did already. That was part A. That was 1/25. And Tuesday would be the same, right? In part A, was there anything special about the fact that this said Monday? It could just as well have been Friday, and the answer would have been the same. Okay, so the probability that the two people were hired on any one given day is 1/25. So that's true for every day, every weekday. And since these are all mutually exclusive options, we don't have to worry about any overlap. So that means that we can just add together their probabilities. And there's 5 of those 1/25. And so that's 5/25, which is 1/5. And that coincides with the answer that we got in the first place. Okay. Finally, for part C, it says, what is the probability that 10 people in the same department were all hired on the same day of the week? And then we want to know if that is unlikely. So here, this is just kind of an extension of the second part. We saw that the first person, or let's restate this hopefully in as easy way as possible. So let's say that there's the first person hired, or let's just pick a day. Okay, let's say the first person was hired on a Tuesday. All right, so that first person will dictate which day it is where everyone is hired. Then we need to figure out the probability that the other 9 people are also hired on Tuesday. So that would be a 1 in 5 chance that the second person is hired on the same day, 1 in 5 chance for the third person, and then that needs to occur a total of 9 times. Okay, for the other 9 people. So this will be a really small number. There's 0.00070 zeros, and then 512. All right, so a super small chance that all those people were hired on the same day. Okay. So we've seen some situations where, like the one with the drug testing, where due to the size of the sample and the size of the population, that we didn't get too different of a result. And it's going to turn out that that's going to happen, especially in some kind of real life scenarios. So we're going to end up seeing under what circumstances we can treat our experiments as if they're independent, maybe even if they're not. So that's what this next part is about. Okay, so it says some cumbersome calculations can be greatly simplified by using the common practice of treating events as independent when small samples are drawn from large populations. In such cases, it's rare to select the same item twice. Like we saw for the drug test situation, we saw, okay, well, it's not that likely to get that first person again. And so that made the probabilities really close. And so what we're going to do is we'll see that if you treat the events as independent, even if they're not really independent, it doesn't drastically affect the result, but it does really simplify the calculation. So here's kind of 2 paired examples that hopefully will illustrate that. So here's the story. A bowl has 14 marbles in it. 8 are blue and 6 are white. 2 are drawn. We want to know the probability that both are blue if the selection is done both with replacement and then without replacement. So let's check. So with replacement first. So both blue. So if they're both blue, that means the first one is blue. There are 14 marbles, out of which 8 are blue. Since we're doing this with replacement, that means when we go to pick out the second marble, there are still 14 in there because we put the first one back, and there are still 8 blue marbles inside. Okay, so let's see what this works out to be. As a decimal, that's about 0.32653. Okay, and then what if we do it without replacement? So still, when we go to select the first marble, there are 18 marbles, out of which 8 are blue. And then when we go to take that second marble out, the assumption is that that first one did occur, so the first one was blue. So there are only 7 marbles, blue marbles still in the bowl, and 13 of them, sorry, 7 blue marbles out of 13 total marbles. So let's see what that gives us. Okay, so that's 0.30769. All right, so there's difference there of about 0.02, right around 0.02. Okay, so let's see, to compare now, we have a bowl with 56 marbles in it. 32 are blue and 24 are white. So one thing that you'll notice between the two scenarios is that the proportions of the different colors are the same. Okay, what I did in constructing the example was basically just multiply the number of marbles by 4. Originally, we had 6 white, now we have 24 white. 6 times 4 is 24. 8 blue, now 32 blue. 8 times 4 is 32, and as you know, 14 times 4 is 56. So I multiplied the number of marbles of each color by 4. Okay, so that just basically makes our population bigger. What we're going to do, though, is the same. We're going to collect 2 marbles out of our bowl, and we want to know the probability that both are blue if we do this selection both with and without replacement. So let's see what happens. So with replacement, okay, initially there are 56 marbles, out of which 32 are blue, and then it's with replacement, so there's still 56 marbles, out of which 32 are blue. So let's see what we get. Okay, 0.32653. Okay, so that is the same as what we had before, right? The with replacement value stayed the same. And the reason for that is because the proportion of whites and blues is the same between the two examples. We just increased the size of the population by multiplying all the marble counts by 4, but the proportion or fraction of them that are blue is the same, okay? We'll see a difference though when we do the without replacement situation. Initially, there are 32 blue marbles out of 56. And then here's where it gets different. When we go to do the second draw, because it's without replacement, there are only 55 marbles left, out of which 31 are blue. Okay, so then we'll see a change here. Okay, so 0.32208. Okay, so now let's see what we have. So we saw with the smaller population, 14 total marbles, that switching from with replacement to without replacement had about a 2% difference in probabilities of getting both blue. It went down from 0.326 and change to 0.307 and change, about a 0.02 difference. Here, increasing the number of marbles to 56, you can see that it's 0.326 and then 0.322 and change. So here the difference is about 4 thousandths, right? So that's much different than 200ths, right? So the takeaway here is that the difference between doing it with and without replacement is going to be more significant when the population is smaller. Our sample size was only 2. It was 2 out of only 56 marbles in the second case. And so the difference between doing with and without replacement was smaller. I'll leave it to you, but if you want to take and increase this number of marbles again, make sure to keep the proportions the same. You'll see that the difference becomes smaller. Or if you make the population smaller, the difference will become greater. Okay, let me know if you have any questions on that. Based on that, we're going to have, our book calls this the 5% guideline for cumbersome calculations. And it says, when calculations with sampling are very cumbersome, and the sample size is no more than 5% of the population, we're going to treat the selections as being independent, even if they actually are dependent. So here, our sample size originally was 2 marbles out of 14. That's 0.14. Okay, so here our sample size was about 14% of the population. So we saw that, yeah, there's this meaningful difference between the two probabilities. In the second situation, it was 2 out of 56, which is about 0.03. Here, our sample size was about 3% of the population. And if you think about it, let's say we had like 1,000 marbles. If we had like 1,000 marbles, the probabilities really would be very close. Okay, so that's the 5% guideline for cumbersome calculations. And we can apply it when we're dealing with a sampling situation where the sample size is less than 5% of the whole population. Okay, so we're going to see an example of that right here. So this one is from our book. So it says find the probabilities, and then we're going to indicate when the 5% guideline is used. Okay, so here's the story. It says in a Prince Market Research survey of 2,518 motorists, 252 said that they made an obscene gesture in the previous month. Okay, so there's 2 parts to this. In A, it says if one of the surveyed motorists is randomly selected, what is the probability that this motorist did not make an obscene gesture in the previous month? So there were 2,518 total motorists. And so if we take away the ones who did make the gesture, that's 252. There's 2,266 who made no gesture. Okay, and we want to know the probability that that person, one selected, did not make the obscene gesture. So out of 2,518 total people, there were 2,266 who did not make this obscene gesture. So that is around 0.899939. Okay. All right, so that's the probability if we take one of these 2,518 persons, the probability that they didn't make this gesture. Okay, now it says if 50 of the surveyed motorists are randomly selected without replacement, what is the probability that none of them made an obscene gesture in the previous month? So if we're saying none of them did, then that means that the first one didn't, and the second one didn't, and the third one didn't, and the fourth one didn't, right? So this is basically an and problem. We're not saying one or the other didn't. We're saying the first one and second and third and fourth and so on did not make this gesture. So that means we're going to multiply the probabilities. Since this is done without replacement, each time we take a motorist out and ask them, or do the survey and say, okay, well, did you make the gesture or not? We're going to leave them out when you go to select the second person. So we've got 2,518 motorists, and 252 made the gesture. So the probability that the first person didn't make the gesture was 2,266, as we saw in the answer to part A. So now if we want the second person, okay, since we're doing this without replacement, we're going to have 2,517 people left, out of which there's 2,265 who did not make the gesture. Then for the third person, it's going to be 2,516 total people and 2,264 people who did not make the gesture. I'll only do one more of these, okay? So for the fourth person, it'll be 2,515 total people and 2,263 people who did not make the gesture. So this is the way that we would have to treat it if we're doing this because they're independent. We have to multiply the probabilities, and they're not independent, they're dependent, sorry. We're having to adjust this size of the population and how many non-gesture making people there are. So we would have to do this 50 times. So there'd have to be 50 of those fractions, and then we'd have to multiply all 50 of those fractions together. And so that's what we mean by cumbersome, okay? Nobody wants to see any of us do that, right? So instead, let's see if we can make that, use that 5% guideline. So we're taking 50 motorists out of a survey of 2,518. 50 out of 2,000 is 0.019. And that's definitely less than 0.05, right? So that means that we can go ahead and treat this as if it is independent, even though it isn't truly. So let's go ahead and act as if it is independent. So if we are, then that means that we could just treat it as if we're doing it with replacement. So it's going to be 2,266 over 2,518 times 2,266 times 2,518. So now it looks like it's starting to be bad again. However, notice that all those fractions are the same and we're repeatedly multiplying, right? So our 50 times, we're going to use an exponent for this. So that's 2,266 out of 2,518. We're going to raise that to the 50th power. Remember multiplication, repeated multiplication, we can replace with a raising values to a power. So this is way easier. Point 0.0053513. Okay. All right. So like a 0.5% chance. So out of the 2,518 motorists, 252, like right around 10%, made this obscene gesture. If we take 50 people out of those 2,500 who were surveyed, the chance of none of the 50 in there making that gesture is only around a 0.5%, and that's what we found out. Okay, so that's how that works out. Just so that you know, in case you were curious, if we had done this humongous calculation at the beginning, if we had done that, it would end up being about 0.004857. So I used software to make that happen, okay? So don't worry about that. But you'll notice that these two values are pretty close to each other, right? We treated this as if it was independent, even though it really was dependent. And it's still about a 1,000th, okay? So our probability is still around only 1,000th apart by making that treatment. All right, so that takes us finally to the end of section 4.2. Let me know if you have any questions on it, and have a great day.